Okay, so welcome to the third lecture. So yeah, just a recap of what we've done last week. Let me try to get this out of the way, just so I'm not confused. So last week we had a bit of a what's going on? Oops. Okay. Yeah, so last week we had a bit of a discussion on like general kind of learning theory. So we derived this nice kind of statistical learning diagram where kind of our general path or like what we want to achieve is that we want to turn data into some kind of function or some hypothesis, right? And in order to do this, we need to we want to kind of let the computer do most of the things, but we need to at least give the computer like some kind of search space on what like possible candidate solutions could be. And so this is what we term the hypothesis set. And so it's basically this approach of learning a search. And so you just have like a big kind of pool of possible candidate solutions, and you just like search through that space. And how exactly you're searching through that space is not really kind of prescribed by this, but the goal is at least prescribed. And so the goal was empirical risk minimization. So the idea is that we have some kind of objective function or some risk function that tells us, how good one or the other hypothesis is on the data that we have. And then based on that, our idea is that, okay, we'll at least so we cannot make the hypothesis good on like unseen data because we don't have this data. But at least what we can do is we can try to make it good on the data that we have, right? And so then this is the goal of empirical risk minimization. And then we had a long discussion on, okay, how good is this type of idea? Should we do empirical risk minimization, yes or no? And then we discussed the bias variance trade-off as kind of basically how do the hypothesis set and this empirical risk minimization idea interact. The more complex of solutions you allow, of course, you will be able to kind of fit your data better and better. But that also means that maybe you are kind of more susceptible to overfitting. Maybe you're taking too much the data into account. And the reason was that you use the data twice. And so you're somehow double dipping, and in statistics, this is always a big no-no. You shouldn't use data twice. But we wanted to use data both to drive our search and also to estimate the performance of the algorithm. And so by being overloaded by these two tasks, this kind of led us into this problem of overfitting. And then we had kind of like a reveal at the end of the lecture about kind of where deep learning actually lives, and actually that the details of how you implement this learning algorithm really affect kind of what happens once you have super over parameterized solutions. So for example, neural networks with billions of parameters and maybe only millions of data samples. And so this was called double descent, and it's kind of one ingredient of deep learning. And but this kind of doesn't appear in this learning diagram. That is just something that is like a detail of the learning algorithm. Today we'll kind of implement or talk more about like what the good learning algorithm is, and identify the learning algorithm that also drives this kind of phenomenon. But we'll first try to walk through like this learning diagram kind of in a little bit more sophisticated way. So the way that we identified risk before was a little bit crude, and so we want to develop something kind of more, kind of statistical. Okay, so the question is, okay, how do we learn? So empirical risk minimization basically establishes a learning goal, right? It's basically formulated to ensure that we can basically work just on the sample. So that's why it's called empirical risk minimization, because we don't have access to the in the actual probability model that the data originates from. We just imagine that the data is like identically distributed from some density. And so the entire idea of empirical risk minimization is that it's a goal that is at least achievable in the sense that we can calculate it on the data. But there's no prescription kind of how to achieve this goal. So how do you actually minimize it? Do you just test all the different hypotheses and you brute force it? Or do you have like some super targeted way to find a good hypothesis? This is not clear. We just know we want to minimize it. And at the same time, also, there's no real indication like what a good risk or performance measure is, which is, I mean, in one sense, it's okay, you might want to have more indication, but at the other end, like this entire learning diagram, that so the fact that learning works, and we had this discussion last week, that like the probability of having like the gap between the training performance and the test performance, in the limit of infinite data is provably going to zero. This is a super general statement that doesn't depend on the learning algorithm. It doesn't depend on the data distribution, doesn't depend on the risk objective that you have. And it's like a very general statement that learning works, which is great. But now if you want to actually implement something, we might want to kind of do some more work and kind of actually try to implement some concrete learning algorithm and concrete risks and so on. And so this is what we'll talk about today. And so, of course, the learning goal is going to be task specific, depending on what you're trying to do. This is how you're going to define your objective. And so there are two kind of broad classes of recurring tasks. So there's like one task, which is kind of the example that we mostly talked about, is kind of the learning to infer something. So to derive some kind of quantity that you haven't measured, or it's, you can also think of it as learning to predict. And so you're trying to generate or to predict unknown data that you haven't observed. And then there's like an entire other branch of machine learning, which is more learning to describe the data that you do have. And so so we said, okay, we don't have the density of the data, we only have the samples. Okay, can you maybe learn the density of the data from the samples, or can you generate new samples from old samples, and so on? And so these are all these like image generation things are more kind of learning to describe the space of possible images. And then once you understand the space of possible images, then you can also generate new ones. And so learning to describe is something we'll kind of talk about later kind of in this course. And so most of machine learning, or like a lot of machine learning, is kind of focused more on this inference idea and kind of learning to predict something. And so this is like if you want to do face detection, okay, you're trying to predict from an image, okay, is there a face in it, and so on. And yeah, so let's get into it. Basically, like so we observe things in the real world, and so all the objects that we kind of observe, very often we kind of understand them to be kind of like a realization, the real world realization of some underlying like concept, right? And so this maybe goes back to like Platonic ideals and so on. There's like some like concept in your mind that has some characteristics, for example, like a human, that is like a concept that you have in your mind, but and then like all of you are like specific realizations of humans, right? But the concept kind of lives on its own. And so the fact is that but the only thing that we observe is the actual realizations of the things, and we don't observe the concept, right? So it's always something that we infer. I look at you, I realize you're humans. And so in that sense, we say that the concept is latent. And so if you look up what latent means, it's hidden or concealed. And so we mean with this that it's a latent variable, that it's just not something we can measure directly, but it's something we want to kind of derive from the data that we actually are observing. Okay, so we want to kind of infer latent concepts. And so here, just like an example, so here like a concept is like a cat is maybe as a part of like a larger kind of class of concepts called animals. And then the realization of this particular of this concept in this particular case was this image, and it's just like pixel values in an image, right? And so we know, okay, from like a given cat might generate some pixel values, and the pixel values are things that we actually observe. And then our goal is to go backwards, kind of go from pixel values to the concept in some shape or form. Here's another example, what is kind of interesting here. So cat is like a member of a set usually, right? So okay, there are animals, maybe they're like whatever 10,000 animals or whatever, right? But it's not like an infinite number of animals. So it's like one of many, but like a countable like a set of things. But then there are other types of concepts, and for example, there's the concept of weight, which is more like a floating point type continuous quantity, right? But we might think, okay, this set of like the banana has some true like weight, and then when we're what we're measuring is like some realization of how this weight interacts with the world, and so maybe we put it on the scale, and then we read off the value of the scale, and then that will not necessarily directly correspond to the true weight of the banana, but because maybe like the way how you construct the scale and so on, there's some noise involved and your eyes are not perfect, and so the actual realization of the value is different than the underlying concept that you're trying to infer. And so by, for example, doing many measurements of the banana, maybe you can actually infer like the true weight by averaging out the variations that you would see. Okay. So then, how do we make this more mathematical? Last week we had this entire discussion that we assumed that our data is stochastic, and the idea was, that we do statistical learning, and so that's why empirical risk minimization involves like expectation values or approximations of expectation values. And so basically, the way that we describe this link between the concept and the realization is like a conditional probability. And so we say, okay, I fix the concept value, so let's say cat, and then there are many realizations that I can generate from this stochastically, right? And then every one of them might be different, but they all kind of originate from the same underlying thing. Like a member of like a categorical latent variable. So there's like a fixed number of categories of animals, but then there's also like this floating point type of latent concept where, let's say, you have like some true mass of your banana, and then you can generate multiple readings of this, and this just captures like all the microphysics that might maybe happen in your eyes and so on. You don't really know what's going on. Maybe there's also some quantum mechanics involved in terms of stochasticity and so on. But there's like a lot of randomness there. So it's the same kind of idea that you have like this conditional probability where we generate realizations from this unknown and unobserved value, and we want to infer this unknown, unobserved value from the data that we have. Okay, so then if you can kind of look into the real world and see, okay, there's like an entire variation of different things, and they all kind of originate from different concepts, and they all, are different realizations of that particular concept. You can kind of think about, okay, how would you describe like the distribution of concepts and realizations kind of jointly? And the way that you would describe this as a kind of hierarchical model. So you first have like the distribution of, okay, in terms infer and kind of basically find out what the latent value is for a given set of observed values. So let's say we have some data X. And the classic way to do it is if you're not in a machine learning class, but if you're like in a statistics class, the way you would maybe do it is, for example, using Bayes' theorem, right? So who knows Bayes' theorem? So seen this formula? Okay. A lot of people have seen Bayes' theorem. So basically it's, like a very simple type of derivation. So you can kind of go here. So here we have the joint distribution on the left, pxz, and so we split it here into px given z times pz, but you could also split it a different way. You can also split into pz given x times p of x. And so then if you just pull down the p of x, then you already have Bayes' theorem, right? And so basically what it tells us, okay, what we want to find out is what's the probability of the latent variable to have a certain value given the data that we have observed. So what is the probability that the thing is actually a cat given the pixel values that we observed? What is the probability that this is the true mass of the banana given the weight, like the reading on the scale that we observed? And so how do we get this type of posterior probability? Sometimes also called an inverted probability. Basically, what we do is we have kind of the data generating mechanism. So how do we generate data? So how do we go from concept to the data, which is p of x given z? And then what is the general distribution of concept values? And so this would be the prior. And then you just have like a normalizing constant, which is the evidence. And so this is normally how you would do kind of statistics. And you can just stick in, if you have like all of these different ingredients, you can do more or less complicated statistics, and then you arrive either at like an exact expression for p of z given x or some approximation and so on. And so this is kind of exactly the content of all the statistics lectures that you might have might not have seen. Okay, so basically this is just kind of one thing that's interesting is that just inference captures both of these things, but then if you go into statistics class, sometimes they use different names for different things. And so, as I said, if it's like a finite set where you have like n different possible values for the concept, so maybe you have like cat and lion and dog and whatever, then this is called classification. So you're trying to take your data and you classify into one of like a finite set of buckets. Okay, is it like this animal or that animal? And then the other option is, okay, if z is like a continuous value, like a real value, like weight or mass, and then it's called regression. And sometimes in statistics, you might think, okay, these are vastly different things, but it's exactly the same. So like these names, they're just fancy names for saying, okay, z is like a real value or z is a member of a set. But like in some sense, it's like exactly the same type of math. And so we'll not make a very strong distinction between classification and regression, even though very often in literature is being done. But you'll see in the derivation why basically it doesn't really matter. Okay. So then the question is, okay, why do you even need machine learning? So as I said, so these are things, so this type of inference is things that, are being taught in like a statistics course, right? So why, linear regression and logistic regression, these things, so they're not like machine learning, right? So why are we talking about this type of an inference problem kind of in the machine learning course? And so the answer is that for standard statistics, we usually have kind of like a closed form mathematical model on how the data kind of came to be. So we know how to go from concept to the data. And so this might be, for example, like a normal distribution. We say, okay, if I have my true mass, the measured mass is going to be randomly distributed, but according to the like Gaussian distribution. Or we might say, okay, my concept is like, what is the probability that it's like a cat? And then if it's a cat, yes, then, I generate some data. And so these are things where you have like some kind of analytic control over, how the data is being generated. And so then you can try to find like various ways to, like statistical techniques. You can do the Markov chain, Monte Carlo, parametric fits, and so on. Once you can write down, with pen and paper, how the data is being generated or how it's related to the concept, then, it's easy. But this requires, so in physics, very often actually we do have like these types of things, because we can understand the microscopic behavior quite a bit. But kind of in the general case, we don't know, like, what is the distribution? Like, okay, what is the distribution of pixel values conditioned on it being a cat? Like, I don't know, maybe, the distribution is more yellow, but I mean, it's a very high dimensional distribution. It's completely unclear what it should be. Right, and so this is really kind of what the gist is. So we don't really have a strong mathematical model for a lot of the data that we actually observe in the real world, and so we only have samples. And so this is a case that we made already in the empirical risk minimization thing. So we imagine, or we assume, that the data originates from some kind of distribution, some joint distribution P, X, and Z. But we don't know what it is. The only thing that we have is the samples. And so we have like a list of things where, like you have two columns, the X and the Z, and then you have like different like realizations of this, but we don't really know kind of what like P animal given image is, or what P image given animal is, or what's the distribution of animals is. So all of this stuff is unknown. And so this really poses a question, okay, how do you even begin doing this if so you don't know P of X given Z, you don't know P of Z, you don't know P of X. And so if you want to do like statistics and you don't know any of these things, it's very difficult, right? And so this is then where machine learning comes in, because machine learning is very good to do things only based on samples. Okay, so then basically our solution is we want to formulate statistical inference as a learning problem. So we, instead of kind of deriving the posterior mathematically, we want to learn like an approximation of the posterior. And so we want to kind of define statistical inference as a learning problem. We need to do our kind of standard steps, right? So, okay, we want to do machine learning, we want to learn something. And so what do we need to do? We need to define a performance objective. We need to define a search space. And then we need to implement like a learning algorithm. And then once we have all of these things together with the data, we get our final hypothesis, right? And so this is basically what we're going to do today. And so let's start with the search space, actually. And so what we are interested in is basically, okay, we want to find or learn the posterior P of Z given X. We don't know what it is. We cannot use Bayes' theorem to derive it. But it's like some object that is out there. And so we want to kind of find it. And so we are applying this learning a search paradigm that we discussed last week. So we just want to look like in a family of candidate distributions. We just want to look for one that maybe looks like this P of Z given X. But it's not absolutely clear that the true P of Z of X is actually in the search space that we have. It probably is not. Right, but we might kind of define our search space in a way that we at least get close to the true posterior. And so this is called variational inference. So instead of kind of saying, okay, I have my likelihood and my prior, and I do like Bayesian statistics and so on, I just say, okay, I know there's this posterior out there. I have like a candidate set of posteriors. Can I somehow get pick like a good candidate that is as close as possible to the true posterior as I can? And so you're turning a problem which is kind of interesting. So in Bayesian statistics, like one of the big problems is like this term, the evidence, because this is a very complicated integral. And so integrating is difficult, but optimizing is more easy. So you're in some sense you're turning also like an integration problem into an optimization problem. Even if you had the true likelihood, for example. And so this is a very popular approach. It's called variational inference. We're just looking for, we're like defining a set of possible posteriors, and we're looking for one that is close to the one that we are actually interested in. All right. Okay, so then how do we define the search space? And so the strategy that we're going to use is basically, okay, we just pick like a specific type of distribution. So let's say like a Gaussian or Poisson or like binomial, Bernoulli, like a bunch of these distributions. And so we just use like a a good type of base distribution, and all of these distributions usually have parameters, right? The Gaussian distribution has a parameter like a mean value and a variance value. And so the way that we're gonna say we do our kind of family of distributions is we just pick like a family like Gaussians, and then we say, okay, the parameters are going to be functions of the data. And then this will basically implicitly implement like a family of Q of Z given X, in the sense that we say, okay, Q of Z given, and then the parameters of this particular distribution, Gaussians or Bernoulli or whatever, they're going to be functions of X. And so in some sense, it's going to be like a family of distributions that are conditioned on X, but they're conditioned through this additional function, how we map the data into parameters of this particular type of distribution. And so this, basically we have a way through this type of construction to go from like a family of functions, which is something we talked about before, you know, with like linear, like perceptrons and so on. So we can go, if we have like a control over a family of functions, we can go to families of densities by just wrapping the function in like a bit of like some density skeleton, right? And so this is kind of how we define our search space of different distributions, and we'll just they all have the right structure, so they have like they're distributions of some latent random variable z, but they're conditioned on x, but they're conditioned through this function f of phi. And so basically searching through the function space means the same thing as searching through the space of possible candidate densities. And so this is kind of what we're going to do in variational inference. Okay, so here just some examples. So we can say, okay, we have a Gaussian distribution, as we said. So the Gaussian distribution has two parameters. It has like the parameter, like the mean parameter and the parameter for the variance or the width of this bump that we have. And so very often we kind of say, okay, the way that we link it to the data in order to make it a conditional distribution, P of Z given X, the way we link it to the data is by having two functions that then kind of take in the data and they spit out the mu and maybe like the logarithm of sigma, right? Or you might have a function that spits out both at the same time, and so on. And so this is one way to link it to the data. There's a different distribution types, so like a Bernoulli distribution, which is kind of the simplest distribution you could think of. It has only one parameter, like what is the probability of success? So it's like the distribution for like one coin toss. Right, and so there's one parameter, and we can say, okay, we'll just have this one parameter, and then it's going to give us the probability of success for a coin toss is 0.5 if it's a good coin, right? But for different situations, it might be a different value. So we'll compute this value as a function of the data, and then in the end, what we get is a distribution. Once we stick this data into the Bernoulli, we get a distribution that has like some probability for success and some probability for not a success, right? And so we basically have something that gives us a binary, like probabilities on the binary outcome. And so that's why basically, if we do variational inference with a Gaussian kind of wrapping distribution, this is what we call regression. And if we do variational inference with the Bernoulli distribution as a wrapping distribution, then this is usually called classification, because basically you say, okay, given the data, you get a distribution like this. And so you say, okay, given the data, I know, okay, 90% is going to be class 1 and 90% is going to be class 0. So this might be cat or no cat, or, phase or no phase, or something like this, right? Whereas here, maybe it's kind of for a regression, it's maybe, okay, given my data, what is the plausible distribution of true weights of your banana? And then it's going to be some distribution. It will probably be centered or like closely related to the thing that you measure. But, there's some uncertainty because your measurement device is not perfect. And okay, so we can basically cast variation, like if we go through the variational inference type idea, all these distinctions between regression and classification kind of also recede into the background. Okay, so then the question is, okay, how do we go from a perceptron to our variation inference? So the perceptron is our favorite artificial intelligence algorithm, very smart. And so here we always had this thing, okay, can we predict whether or not somebody is a good basketball player. We have two features, like the height of the person and the age of the person. And the way that we did it so far is that we have kind of like a linear decision boundary, which is given by a linear function like this. So you have the sum over, like some weighted sum over the input features, and then some overall kind of shift, which is the bias. And then we said, okay, if this value is like greater than 0, we'll say, okay, it's class 1. If it's smaller than 0, it's going to be class 0. And so we're basically splitting the input space into two specific values, 0 and 1, right? But what we're now talking about is that we want to not only have like predictions 0 and 1, we want to basically have like more information. We want to have like an uncertainty measure, like how convinced are you that this is a good basketball player, right? And so that might be not a value between 0 and 1, but it might be more, you know, like a probability between 0 and 1. So is it like 90% a good basketball player, or 10%, and so on. And so basically what we want, or what variational inference can give us, is it will give us a more detailed answer. It will give us a degree of confidence in the prediction that we have. And so instead of splitting the input space into two strict disjoint sets, we actually kind of have like a gradient where kind of to the left hand side, I mean, it's still kind of like a linear decision boundary of sorts, but there's a kind of like a smooth transition between your confidence in being a good basketball player and a bad basketball player. And so that's maybe a little bit more kind of reflective of your actual belief, right? So like you don't really know whether or not somebody, you know, what the skills are, but you know, you might have some kind of hunch. Yeah. Now how we learn our theory. So we're not learning it. So basically now we're only describing it in terms of probabilistic terms. So how we learn like a right decision boundary, this we'll get to this. Yeah. So if you want to, well, so you plug it into your functions here. So you say, okay, if you want to say, okay, what is my conviction like percentage of, you know, are you a good basketball player? I'll take your features X, I stick it through these functions, right? And this will give me like a value of 0.8. And then this gives me a distribution. So good basketball player, yes or no, given like chance of success of being a good basketball player of, you know, 80%. Right. Yeah. So, or once you've selected a good f of x, this is your kind of gateway into making probabilistic statements. Okay. So, yeah, so kind of binary classification, as we discussed, so this was kind of the example that we just were talking about. It's basically uses the Bernoulli distribution as the base or wrapping distribution. It's the simplest possible distribution, as we discussed. So here, kind of the possible outcome values, or the true values of the concept, are 0 and 1. And so as a basketball player, so either you are a good basketball player or you're not a basketball player, but we don't know because it's latent. We don't know what the true value is. But what we can say is, okay, given the data that we have, we can derive a posterior, which is, you know, P of Z given X. And the way that we derive this posterior is we need to, find a good family of distributions that has the right type of Z. So, you know, like a two-class category. And then, but in order to kind of link it through the Bernoulli, we need to find like a function that takes an X and, that gives me a value between 0 and 1. Right, and then this is the way that I do my variational inference. Okay, so in order to kind of make this type of variational approach, so we basically need to find a family of functions that kind of maps X into this parameter of the Bernoulli distribution, which is can only have values between 0 and 1. You can have not like a Bernoulli distribution with chance of success of 120%. Right, and so we need to somehow define functions between 0 and 1. And so what kind of is most easy to have like functions between the real space and the like unbounded spaces, but where like the functionality can be from minus infinity to infinity. But we can very easily like convert a generic function, any function into a function that only outputs numbers between 0 and 1 by using what's called like a squashing function or a sigmoid function or logistic function. And so it has like this structure here. It's 1 over 1 plus exponential to the power minus a. And so you can see what's going on. If it's infinite, then this is 0, and if it's plus infinite, it's also quantity, right? And so that might be kind of like a factor 2 missing, but yeah. So basically, you can take constrain a function that has like a infinite range to a function that has a finite range without any problem. Okay, so then how do we do this? Basically, we have a very simple recipe for classification. So basically, the way that we do it is, okay, we have our data x, and then we run it through a function that maps from the real high-dimensional real vector space to the space of reals in the 1 dimension. So this gives us a kind of 1-dimensional function between minus infinity and infinity. And in order to make it a good function that can map into the parameter of the Bernoulli distribution, we squash it using the sigmoid or logistic function. And then we're done, right? And then we can stick it into our Bernoulli, and we have our variational inference procedure. Okay, so then the simplest, so what kind of function can we look at? And the simplest possible function are linear functions. So this is exactly the type of function that we've discussed in the perceptron. Basically, we have a function that is like a product between our weights and x. So there should be an x here. Let me try to fix this actually. Right, so you have your kind of basically inner product between a weight vector and your feature vector plus your bias b, and so you can also kind of write it in the vector type way. And so then the way that we kind of formulate our family of distributions is that we have our Bernoulli wrapping distribution, and then our parameter is going to be the sigmoid of the linear function, right? And so this is exactly kind of what we discussed, and this is the simplest possible neural network. In some ways, it's already a neural network, and it's basically like a variational inference version of the perceptron, which we discussed in the first lecture. Okay, so then we can kind of see what's going on. So how does the perceptron really relate to the variational inference? Basically, our input function before the sigmoid, which is sometimes called the pre-activation, gives us kind of these diagonal lines, the isocontours of constant wx plus v, right? And so whereas the iso surface where this is 0 was our previous decision boundary, right? So previously we had, okay, wx plus v is greater than 0. We said, okay, it's one class. If it's smaller than 0, it's the other class. So this is kind of like this decision boundary. But then we have like different types of possible iso levels. And then we basically have like our sigmoid wrapped around this. And so this is how we get this gradient. And so if we look at this point, we have our function as a value of x, right? We stick it through our linear function, we stick it through our sigmoid, and then we stick it through our Bernoulli distribution, and then we get our Bernoulli distribution, which just has like 2 probabilities. And then so here in this particular case, it's going to be very confident that it's like green. It's a good basketball player. Here, it's kind of unsure. It's exactly on the decision boundary where it's this is 0, and so there, the squashing function is 1/2, right? And so here we go from 0 to 1, and so it's exactly 1/2, and so it's completely undecided. And then further away, it's very confident that it's not a good basketball player. And then the isosurface is very negative, and so that's why once you convert it into a Bernoulli distribution, it's very confident that it's kind of the class 0 prevails. Okay, so this method is model is very well known in the statistical literature, and so this is called logistic regression, right? So as I said, so sigmoid is kind of like what's called the logistic function, and so linear binary classification in the machine learning point of view is just the same thing as logistic regression, right? And so there are jokes going around that machine learning to a large degree is kind of like nonlinear logistic regression, which is true. But so we're not at nonlinear yet. So the only thing that we know right now is linear logistic regression. Because why linear? Because this thing in the sigmoid is a linear function wx plus b. Okay, so we kind of defined our search space, so we know how to construct like a space of possible distributions. And so now the question is, okay, what else do we need to do? We need to define a performance objective, and then we need to implement a learning algorithm. So let's try to do that. So what is a good performance objective? And so now, like the things that we're trying to optimize, like the objects that we're playing with are probability distributions. So this is a space of possible probability distribution. And so we need to somehow define an objective as a function of a probability distribution, which is not very kind of easy, but we'll manage. And so in order to kind of do this variational inference thing, we need to somehow pick a good distribution that is close to the true distribution. So really what we need is some kind of distance measure that somehow captures the distance between distributions, right? So and so that because distributions are complicated objects, the distance between distributions might also be a complicated object because it's not just one number, but so let's assume we have such a distance, then we have kind of like a clear learning goal. Okay, we want to minimize the distance between the estimated posterior and the true posterior. And so that's easy to say, but then we also need to make sure that we can compute this distance using the empirical data that we have, so empirical risk minimization and so on. But we need to first find, okay, what is like a good distance functions between probability distributions. And so here's just an example why this is not like an obvious thing to do. Because distributions are extended objects and not single points, like a distance needs to be something more involved. So these two distributions, the mean, so I mean, you could imagine, okay, I'm comparing distribution by comparing their expectation values, right? So that's kind of, like a workable ansatz at least. But both of these things have the same distance and expectation values, but they're vastly different distributions. And so, if you're asking, okay, which pair of distributions is closer, what would you say? Do you have any preference? They're different in different ways. Who is for the one on the right? Okay. Nobody, there's nobody. Is there anybody for the one on the left? No. Okay. Yeah, so your instincts are correct, at least. Well, I mean, I don't know. It's unclear. So let's see where we go. So basically, one idea that you can have is that you just kind of sample the space because the distributions, they kind of describe like a possible space of outcomes, right? And so one idea you could have is saying, okay, I want to kind of look at all the possible outcomes, and then at each possible outcome, I compare, what is the probability for this outcome? And if it turns out that for a lot of possible outcomes, also the distributions are very different, then that's an indication that the densities are different. And so on the left-hand side, for example, here you have a super big difference, so this is essentially 0. And so here you have a finite density. Here it's the same way, the other point around. Actually, here there's one point where there's basically no difference between these densities because they're exactly the same density, the point where they cross. And so there are like areas of big difference and areas of little difference. And so if you have very similar distributions kind of across the board, you have very little difference, right? And so the question is, okay, how can we capture this mathematically? So one way to capture the density or the difference in height, if you're like at a specific point, is that you can just take the ratio of the densities, or you take the ratio, the logarithm of the ratio, which is actually like the difference in log probability values. And so this is kind of like a way, so once you are at a point, can you decide if it's a big difference or is it a small difference? You can just compare the ratio of these function values, right? And so that's kind of doable. Now the question is, okay, how should you weight the different x values? There are infinite number of x values, and so clearly, I mean, you cannot just look at everything, and so at least not all the points are created equal. And so the question is, okay, how do you do it? And one of the things or ideas that you can come up with is that at points where the density is large, because this is a point where you have, you happen to have a lot of data, or, it's quite likely that you have data there. If the densities differ there, it's a big problem, or it's a very noticeable difference. Whereas if you're like the place where both of these densities are kind of small, and okay, there might be differences in the tails, but maybe you're not so, maybe you don't care so much because it's in the tails and you'll hardly have any data there. And so you can kind of basically imagine that you want to have some kind of weighting function which treats some x values with higher importance than other x values. And so you want to have some weighting function, and then you weight the differences in densities according to this weighting function, then you integrate over the entire space, and then this is going to be your global distance measure. And so there are very natural candidates for the weighting function, so you can either take Q or P, and then this leads to a construction called the Kullback-Leibler divergence. Has anybody already heard of this? Yeah, okay, so if you're in the statistics lecture, you probably know. And so it's basically like a distance measure between two densities. And so it's expectation value. So here you take the same weighting function, which is in the numerator, and then this measures the discrepancy between two densities. But it looks at the differences between the densities through like a specific lens of one particular weighting function. And so if you would use Q as a weighting function, it's different. And so it's a very important point, which is unusual for distance measures. It's a non-symmetric distance. So the distance between P and Q is different than the distance between Q and P. And the way that I like to imagine this is, okay, if you're as a human trying to decide is something close to you, yes or no, it clearly depends on who you are. So, if I like reach out my hands, my natural variance decides whether or not things are close to me. If you're like a child, like you have little hands, or like T-Rex, like there things are farther away, even though like objectively they're like the same, same distance away. If you're like Shaq, you have like huge hands, and then a lot of things are close to you. And so it really depends on the kind of variance of this base distribution on whether or not something is close or far from you. Okay, so then this is KL divergence, one of the most used kind of distances in statistics, and so make sure you can understand these correctly. And so when we go back to our learning problem, so now we kind of have like a natural objective. So we want to minimize the KL distance between the true posterior and the approximate posterior. So we say, okay, we have a space of our possible posterior densities, or at least approximations to it. And so we want to minimize the distance, the KL distance between the true one, which is in blue, and then the approximation, which is in green. And so that seems like a natural way to set up this learning problem. And the problem is, of course, we don't know P of Z given X, right? And so, okay, great, we found like a nice metric. It's going to be 0. If we really find the true posterior, it's going to be 0. Excellent. But in order to compute this thing, you need P of Z given X. Okay, so we, again, like the same way, like in the empirical risk minimization, we found like some nice construction on what we would like to minimize, but it turns out we cannot actually compute it because, okay, if we knew what P of Z of X is and we could actually do this integral, then, okay, why are we doing machine learning anyways? Because this is the thing we want to find out, right? And so if we had the posterior, we would not need to do machine learning. If we want to do machine learning and want to compute our performance measure using the thing that we're looking for, something is wrong. And so the question is, okay, how should we compute this? And so we don't know P of Z given X. We don't even So, and this is already like the inference results is even the more complicated version. So we don't even know the ingredients to calculate P of Z given X using Bayes' theorem. And so there are lots of obstacles in the way. And so you might imagine, okay, maybe sampling works. So you could actually figure out, okay, do I actually need to have, there's also a typo here, sorry. So let me just fix this quickly. Z given X, all right? So, okay, so let's say we have our KL divergence, right? And so you say, okay, do we actually need to evaluate P of Z given X? Is it actually true that we need it? And you might say, okay, well, so I want to optimize this KL divergence with respect to the parameters phi. So I don't actually need to evaluate, this is just going to be some kind of constant factor, so some P log P integral. So this is constant, doesn't actually depend on the parameters. And so actually the only thing that I want to minimize is this integral, right? And so we know basically, okay, how, okay, we still have the problem. Okay, so this is the thing we can evaluate. We got around evaluating the numerator because it's not really relevant for the minimization. And we already know from our risk minimization tricks that we can get around this thing, this expectation value, because we can just use samples, right? So instead of doing the integral, we can just do Monte Carlo thing, Monte Carlo sampling from the posterior, and then we would be able to compute this just fine, right? And so in some ways, we already kind of did one step. The problem is that we also cannot sample from P of Z given X. So not only, I mean, we don't know it, and then as we said, probability densities are always kind of two phase things. So they're a function that we can evaluate, but then they're also a thing we can sample from, and we cannot do anything about the posterior. So we don't know the posterior, we cannot sample from it, and we cannot evaluate it. And so it's a nice idea, but it doesn't work. Okay, but it actually there's a very, very like elegant trick. So somehow the problem becomes easier by making the problem that we're trying to solve more complicated. And so what we're talking about is, okay, we want to do kind of inference for, we want to get this KL divergence for a particular X, right? So let's say I give you some data and we want to say, okay, what's the posterior of X? And we want to do variational inference to find a good posterior for this particular X value. Yeah. Yeah, there should be like a minus. Very good. Minus. Yep. Good point. Yeah, because exactly. Okay, so so for one particular X, it's very difficult because we cannot sample from this posterior because we don't know what it is. But now we can kind of see, okay, what happens if we just want to solve it for all the X in the world in one go. So we basically want to train or learn our posteriors once. We want to learn like a generic function. I mean, what we want to do is like a generic function f of X. And then we want to be, so this would allow us to estimate the posterior for all X at the same time, right? It's not like you're, I give you an X and you do like some statistics to interpret this X, and then I give you a different X, you do some statistics, but I give you like a bunch of X's and Z's, and you do machine learning, and then you get like a function f of X, and now you can just, for any type of X, it's a very fast process. And so this is so this approach of solving statistical inference, so getting the posterior for all of the X's at the same time, is called amortized variational inference, because you basically pay a lot of effort kind of upfront, but then every subsequent type of inference is very, very fast. So we do training to get this f of X, but then once I give you a new X, you just stick it into your f, and then you can do statistical inferences very fast. So this is called like amortization. And so it turns out that the thing that was impossible before to calculate this KL divergence, once you go to this amortized setting, where it's actually like a more complicated problem because you try to solve it for all the possible X's in one go, it becomes much, much more tractable. So why is this the case? Because let's say, okay, we need to declare our more ambitious goal. So not only do we want to minimize the KL divergence between the posterior and the approximated posterior, but we want to minimize it across the board for all possible x. Right? And so we basically, one approach would be that we want to take the average KL divergence that you get, so the average distance between your approximation of the posterior and the true posterior, once you average over all possible conditioning values x, should be on average small, right? So on average, you want to be like a good statistician. And so if you write this down, you basically add like one level of integral on top of this, so you integrate over p of x. Then from our KL divergence, we get this point p of z given x, right? And so now this is actually something we can estimate, because now magic happens, where basically we're saying, okay, well, just like this integral over x and z given x is nothing else than just the integral over the joint. And how do we know how to remove this integral from the joint using samples? We can just sample from the joint, which is the samples that we have, and then we can just estimate it using like an empirical estimate of the integral, right? And so just to kind of recap, so if we just do this integral without this, it's very difficult because, okay, you cannot solve it in closed form because you don't know what p of z given x is this function. You cannot solve it using kind of sampling method because you cannot sample from p of z given x. But now once we add this wrapping thing, somehow things simplify, and we say, okay, it's just requires an integral over the joint density. Okay, it's not something we know, but we know how to get around this because we just have samples from the joint density, which is our training data. So our data and the labels that we get, like the pixel values and the animal type and whatever, and we can just calculate this thing. And so this is kind of nice. So by just making the problem more ambitious, it became easier. It doesn't happen very often, but in this case, it happens. All right. So this took a bit of time to develop like what exactly our kind of performance measure is going to be, but it's also kind of more richer version of performance measure, and it's not just like counting errors as we did like in the last couple of lectures. And so we arrived at a pretty simple way to do our to set up our learning problems. So as we said in our empirical risk minimization, we need to have like some data distribution. In our case, it's the data is like labeled data, so you always have two things. So you have your actual data and the true label, right? So like the pixel values, and so somebody tells you this is the cap. And now this is basically we can set up our empirical risk or like the true risk, which is the expectation value, and we approximate the true risk with our empirical risk, which is just like this very simple construction. We just evaluate the log probability of the estimated posterior under the data samples that we have. And so this is sometimes also called the cross entropy loss, because you have, so this is like a construction that's called like information entropy. And so it's a cross term because you have one density here and a different density here. All right, so we can go back to our plan. So we have two things now. We have our performance measure and we have our search space. And so now we just need to find a learning algorithm. Okay, how do we actually optimize this thing? So we ensure we can actually calculate it, so that's great. But now, how do we make it better and kind of find like a good final hypothesis? And so let's look at this. So which of these is better? Who's for the one on the left? Okay, everybody. Nobody's for the one on the right. Very good. So you have good instincts. And so the question is, okay, how do we, let's say we pick like a random hypothesis in our search space, right, of possible distributions. We just pick one. And the question is, how do we get from this one to that one, right? So we know that this is better, but nobody's going to tell you how to get from this, because you just like dropped in. It's like the computer game you spawned in your search space. And so now how do you find and navigate the space? And okay, so we can kind of see, how our kind of risk measure is going to be. So basically, the way that we have it set up, so we're kind of summing up the probability, and so the way that we sum it up is we derive this posterior density using our x and whatever setting we have, and then which probability do we take? We take the probability of the label that we got in the data, right? And so we can say, okay, let's say for this point, it's going to be very, very confident it's green, and in fact it's also a green label, so we get like a huge boost. So it's a high probability, and the high probability is good because this is because of this minus sign, it's gonna reduce our loss a lot, right? So having high values in this posterior probability is very good because it says it matches the confidence of the algorithm matches the actual label, right? And so we can just see, okay, there's like a few things where it's like half confident, then this one on the very right is maybe kind of it's slightly misclassifying. It's more confident. It's kind of in the red region, but it's kind of fine. And then for the red point data points, it's the same thing. We always take the posterior and we pick up or we compare the true label with the confidence score of the posterior estimation, and so we can just pick up all of these different probabilities and we just sum them up and equip them with a minus sign. And so here so the nice thing is here you see fairly large probability values because there's a nice coordination between the true label and the confidence score. And so for the other one where you correctly estimated it's wrong, so you can just convince yourself that the way that we set up our performance estimate indeed also indicates that it's bad, because here we always have kind of mismatches. So we have the true label is here, but the machine learning algorithm is very non-confident it's actually red because it's exactly flipped around, right? And so the thing that you actually pick up from these posterior distributions using your performance measure, they're all like small probability masses, and so because of the negative sign, so this is not good, right? And so you can basically go compare, like you have a lot of like large contributions that go into the negative direction, that you have lots of small contributions that go in a negative direction. So this matches your intuition that the left-hand side is correct, and so we are kind of confident our performance measure makes sense. Okay, so then we have basically for this very simple neural network, we have a space of 3 parameters, right? For perceptron with 2 input features, we have W1, W2 for our kind of little inner product between the weight vector and the feature vector. And then we have our bias term, which shifts everything. And so the question now is, how should we find optimal values for our weights and biases? And I think this is already something we just, or somebody had a question, okay, like even with the perceptron, how do you find good values? So I think in a tutorial session, I asked you, okay, can you try to find one? You can try to brute force it for 3 variables. It's still possible to kind of brute force this. But then, is there like some nice way to find good values? And so the key idea is that we don't need to kind of arrive at a good value at one go, but it's fine if we can kind of step-by-step optimize or like slightly improve our hypothesis. And then if you're just iterate this a lot, you improve, and then if you do this like a sufficient number of time, you'll kind of get at a sufficiently good solution by just iterative improvement. And so in the last lecture we had this idea of an iterative training loop. So you have like some kind of initial guess, you just get dropped into this landscape of possible solutions, and now you start improving step by step, and you just say, okay, maybe I give myself 10,000 steps, and then I just improve 10,000 times, and then you find like some good solution. And so the way is, okay, you get your examples, you evaluate your risk, and then you figure out, okay, is there like a nice way to adjust my hypothesis in order to get to a slightly better solution? Okay, so we need to have like a rule for like a small adjustment. So okay, which ways of we have our function, as our empirical risk, we want to minimize it. So clearly, we want to get to this point. And so let's say we initialize and we arrive here, and then now the question, okay, do you go left or do you go right? right? So for you, it's obvious because you see the entire function, it's clear. Okay, obviously you should go to the left. The problem is you don't know. You just get dropped into your landscape. Like it's, maybe like with a helicopter, you get to like dropped into some national park. You don't know. You don't have a map, and so you don't know. You just know your current value, right? And so now the decision is much more difficult. Like, do you go left or do you go right? You don't know. You just have your local value, and what are you going to do? It's a bit hopeless if you don't have any other information. And so you might already know where this is going. A function has much more information locally even than just the function value. And in particular, like a very good piece of information is the tangent. So locally, if you're on a mountain, you will know like in which direction does it go upwards and which direction does it go downwards. You don't need to have like a map of the entire national park. You can just look at your feet and you'll know kind of which direction is like downhill, which direction is uphill. And so basically, this is local information, and it's very useful because even though that you don't have any global information, you just look locally and you can say, okay, like to the right, clearly like somehow the function is going uphill. And so this is not the direction I want to go. So I want to go opposite to the gradient. And so I want to go left, right? And so having gradients is very useful. And so this gives us a kind of like a stupendously obvious optimization rule. So gradient descent is what's called like a first order optimization. So first order means that you not only have the function value, but you actually have also the gradient information. And then it's a simple rule of walking downhill. And the only question that you need to ask yourself, okay, how big is your step size, right? So do you take, okay, you say, okay, clearly I need to go left. And so do I kind of jump left or do I kind of tiptoe left? And so this is what's called the learning rate. And this is the way that we kind of continuously improve our hypothesis. And then the hope is by just improving, many times, you just arrive at your empirical risk minimum. Okay, so that's gradient descent. And so then the question is, okay, how do you tune the learning rate? And so, as I said, so you can tiptoe, and this is very conservative, but also very computationally expensive because now you just need to do many steps. So 10,000 steps might not be enough. Maybe you need to run like 1,000,000 steps. And every time you want to decide which way to go, it's, you need to evaluate the function and the gradients, right, which is costly. And so basically saying, okay, left, and then you go like a millimeter, and then it says, go left again. And it's like, you're not being surprised, and it just says left. And like at some point you might say, okay, fuck that, I'll just go faster, right? And so you could say, okay, let's go very fast. And so you could go left and you just go like a kilometer left, like blind, and then you see, okay, what's your empirical risk? And then might turn out, okay, maybe it's smaller, but also might mean that it's larger, right? So you might say, okay, I'm going left. Okay, you overshot, and now it's saying, okay, go right. And so now you go right, and then suddenly you even like have like a larger value than what you had before. And then you go left again. And so if you have a very large step size, because this is local information, the larger your step size is, the more you're trusting that the global structure matches the local structure, which might not be the case. And so if you kind of think about like Taylor expansion and so on, the reason gradients are good is because it's like a first order approximation of the function in Taylor sense. If you had second order derivatives, you would know the curvature. And so there's like an entire class of second order optimization algorithms where you have like the Hessian matrix, for example. But yeah, so basically how much do you trust that the local structure correctly matches the global structure? And then usually what's happening is that there's like some kind of optimal learning rate where, you're maybe kind of trusting your local structure a bit, and you have like some intermediate step size, and then you quickly arrive with few iterations at your minimum. And then, so we'll have a larger lecture about optimizers and deep learning. And so there are lots of things, and what is it if it's like not like a simple function like this, but maybe you have like a hill, and so you don't want to get stuck on the local minimum, and so can you like kind of shoot over this thing? And so there are various tricks, but so this is like the basic idea of gradient descent. Okay, so in order for gradient descent to work, it's not surprising that you need to have differentiable functions. So you actually need to have gradients. And I think one of you commented that like a perceptron doesn't have good gradients because it's basically like a piecewise constant function. So what is the tangent value for a perceptron? It's always 0, right? So it's always constant except for 1 where it's infinite, right? But that's not like a useful function to compute the gradient of. And so like just this kind of 0-1 loss where we just counted errors is not actually useful to have like gradient descent. And so, but what's nice is through this entire construction for variational inference, we also made our kind of loss function differentiable. And so we can actually use gradient descent. And so if you have your empirical risk, basically we have two things. We have this one function which computes from the data the parameters of the distribution. So this is this f of phi given x. And so this matches to theta, and then once you have theta, this goes to your wrapping probability density into your empirical loss. And so if you have a differentiable loss and a differentiable function that maps from the data to the parameters of the density, so like this f of x, if this is differentiable, and this entire construction is differentiable, then the whole thing is differentiable, like simply through the chain rule. All right, and so for the perceptron, this is actually doable by hand, and so this is one thing we'll basically do in the tutorial. So you'll write the gradient descent, like a gradient computation by hand, and then you'll quickly learn that this is very annoying and it's very error prone, and you'll never want to do it again. Then this motivates, that we get some smart systems to compute the gradients for us. But I mean, for a perceptron, you can imagine it's not like a complicated function. It's a linear function. How do you differentiate a linear function? You know how to do it. And sigmoid is also easy to differentiate. The logarithm is easy to differentiate. So you'll be able to do this by hand. But it's even like this simple function is going to be super annoying to actually code up. Then, all the frameworks, like machine learning frameworks, they're basically frameworks that make it easy for you to compute these derivatives so that you don't need to do it by hand. So TensorFlow and PyTorch and these things are gradient computing frameworks, essentially. Okay, so to close out the lecture, just an example that we can actually do it. So this is hopefully what you'll get in your tutorial. So here we have gradient descent. So we start off with a very bad perceptron. And then as we're iterating, it becomes a nicer perceptron, right? Because the function is not becoming nicer because our function class is linear separators. And so, but for this particular problem, linear separation is nice because it's almost linearly separable. But you can see, okay, it doesn't really matter how you initialize it. If you just optimize, it will figure things out. And it's a general learning algorithm. It's not dependent on the data distribution. It will work for other data distributions as well. So in which direction will the optimal decision boundary be? Like this way. Yeah. Let's see if gradient descent finds it. Whoop. Nice. Okay. So you can see, okay, now it overshot a little bit. And it's kind of slowly self-correcting. Okay. So gradient descent worked, and so we now have actually a machine learning system, right? Before we had decision boundaries. We talked theoretically, okay, bias variance trade-off and minimization and so on, but we never actually knew how to optimize this. And so in the first tutorial, we had something you could measure the performance. But you couldn't use it to optimize it. And so now with gradient descent, you can actually, make this actually learn. And so let's say, okay, we have this, it looks very, very good. We have this, doesn't depend on the data, but actually it turns out, so we found a nice way to optimize perceptron inference machines. But as we've seen, it's not a great AI, right? It's a pretty dumb algorithm. We can optimize it. So within its dumbness, we can find the best one, kind of the best candidates among all the bad ones. But ideally, what we discussed last lecture is that we want to increase the complexity of the function class, right? And so that means that we can kind of go nonlinear. And there was a bit of discussion, okay, should you overshoot in complexity? What's the right complexity? But clearly we want to do something more complex. And so here's just an example of like a famous benchmark data set in machine learning. That's called the half moon data set. And so this is clearly like not a linear decision boundary. And so you can do machine learning with the perceptron on it, but it's gonna be, I mean, it's gonna do like the best job it can, but it's not gonna be very good, right? And so you end up kind of misclassifying quite a few points. Like here you can see the contour lines are already blue, but there are lots of points that are going to be misclassified. And so ideally what you would want is to have like some kind of S-shaped nonlinear decision boundary. And so this is kind of the beginning of deep learning, that we want to have something that is non-linear. Okay, so then so problems that remain. So we made some good progress. You know, for the first time, we can actually train artificial intelligences. You know, we have our perceptron-like thing. But for the next steps, what we need is, okay, how can we build up arbitrarily complex functions? You know, I don't want to kind of think about the data problem every time and say, okay, like this might be a linearly separable problem. This might require like a whatever polynomial or so on. I just want to have like some general machine that can basically express a very wide range of function. And it's going to turn out that this is exactly what neural networks are. They're basically large families of functions. And for these complex functions, I also kind of expect that the gradient computation is going to be complex. And then the question is, okay, how can we get those gradients easily? And so I already hinted at it, that there are frameworks that allow you to do the gradient computation so that you don't need to do this by hand. Believe it or not, people like a couple of decades ago, they wrote a paper. This is my new neural network architecture, and they had like pages and pages of the gradient calculation in the appendix, and so very error prone. And so fortunately, we don't need to do this anymore. Okay, so that's what we had today. So just one bonus point. So we had this talk about double descent, and so we had this discussion that, okay, once you are so over parameterized that there are many solutions that are perfect, have perfect performance on the training data sets, the empirical risk minimization is not sufficient anymore to differentiate between good solutions, right? They all have perfect performance. And so now it really depends on how did you do the optimization. And it actually turns out this entire phenomenon that you have the second descent is very tightly linked to the fact that you use gradient descent as optimization algorithm. If you use brute force or like some other like random walk, you would not see this. But if you use gradient descent, it's kind of the has the right what's called implicit bias to pick out a good solution for you. And so that's quite interesting. Okay, so that's what we had for today. And then see you next week. So we have a few questions.
The last slide.
Yeah. 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 So there's like an entire valley of connect, and they're like flat directions. And so that's kind of nice. So a lot of like the optimization literature, it's about like convex optimization, where it's basically you have like a nice bowl, and then you can kind of reason about it in a nice way. It turns out in the super high dimensional space, almost all problems are non-convex optimization problems, and so then these things appear, right? Because you have like these flat directions and valleys of things.
So almost all of that.
Yeah.
What are the assumptions?
Well, I mean, the assumptions of when this appears, or
like when connection,
yeah. So this is it really depends. So it's not an easy question to answer, because it's depends on the network architecture. So every network architecture will have. I mean, it's very easy to construct. It's not that every high dimensional function has this nice property, right? I mean, you can think of high dimensional function with like wiggly things and like lots of local minima, which are each like convex on its own and don't have any connected minima. And so it's some like combination of how you define your loss. So like in this, so what is the loss landscape here? So it's like the loss function itself, but then it's also like the mapping function from the data into like the parameters and so on. And so like, okay, there's like some interplay between the network architecture, this F, what do you use for F, what do you use for L, and so on. And so these might produce minima or might not produce minima. And so it's generally not an easy thing to answer. What people try to do is that there are like a few techniques, but we'll talk later about is there are some attempts to try to shape the loss landscape in a nice way. So for example, that you smooth out any local minima. And so these are called like regularization type things. So this is like a very, very kind of from a statistics point of view, from first principle derived loss function, right? This KL divergence. But actually it might turn out that the loss landscape, if you use this to literally, becomes intractable. And so you can add like multiple terms, which make this a bit smoother. Maybe then it's not actually the posterior and so on, but it's easier to optimize. And so a lot of like network architectures are kind of meant to smoothen out the loss landscape. Any other questions? Okay, if not, then I'll see you Monday, and so maybe I'll try to upload the exercise before, because you'll try to optimize, get this gradient descent working, and you can already think about what these derivatives would be for the perceptron with the sigmoid, and then if you have this written down, you can try to implement it in code. Okay, thanks a lot. Bye bye. Okay.